In this video, we will introduce our prototype of a reconfigurable battery board. This battery board serves as an evaluation testbed to support the research on reconfiguration-based energy optimization in battery-powered systems. In reconfigurable battery packs, the connectivity among battery cells can be adjusted. In this way, we can control the discharge pattern of individual cells and thus to improve the system performance. Furthermore, we can also address the cell unbalance issue by controlling the system configuration, and we can also bypass those failed cells when necessary to improve the system reliability. An important problem in this direction is to identify the optimal battery configuration based on both the real-time load requirements and real-time cell states. Our battery board serves as an evaluation testbed for research in this direction. This is an overview of our battery board. The battery board consists of 4 individual battery cells, and an I/O module is utilized to send a control signal to the board. We also have a power supply for the I/O module, and a USB converter is utilized to connect the module to the controlling laptop. In the battery board, a few relays are utilized to realize the system configuration flexibility, and the connector is equipped on each battery cell to receive the controlling signals. The battery board also has 4 expansion interfaces, which allows us to increase the system scale when necessary. In this demo, we will show how this battery board works. This is an implementation overview of our battery board. Here we have this 4-cell battery board where the connectivity among these 4 cells can be adjusted. And we have these supplementary components to pass the controlling signal to the battery board. And we have this controlling laptop to determine the desired configuration among these battery cells. To clearly show the effect of system reconfiguration, we use these 2 bulbs as the load. In this way, the different voltage output from the battery board can be reflected by the different brightness of these 2 bulbs. We use 5 different configurations as an example. In the first configuration, the 4 cells are connected in serial, and thus the output voltage of the battery board is the sum of the individual battery cells. In the second configuration, the first 3 cells are connected in serial, and then the 4th cell is left unused. The third configuration also forms a 3-cell battery string, but with the first 2 and the last cells instead. In the fourth configuration, the first 2 and the last 2 cells are connected in serial, and then these 2 battery strings are connected in parallel. All these 4 cells are connected in parallel in the last configuration. With these 5 configurations, the first one outputs the highest voltage to the load, and thus the brightness of the bulbs in this case is the highest. On the other hand, the last configuration outputs the lowest voltage level, and thus the bulbs shows the lowest brightness. Let's start with the last configuration, which supplies the lowest voltage level to the load. We can see the 2 bulbs are hardly lightened in this case because of the low voltage output. And also, the ticks we hear is because of the relay operations in the board, and we intentionally make the delay between 2 relay operations longer to make them more observable. The lightness of the 2 bulbs increases with the 4th configuration, and it increases further with the 2nd and the 3rd configurations. The lightness of the bulbs reaches highest level with the 1st configuration because of the highest voltage output levels. With this testbed, it is possible for us to adaptively control the discharge pattern of battery cells according to both the load requirement and the cell state, and thus improves both the energy efficiency and the system reliability.